we'll pick up from looking at work and now consider looking at it from a completely energy point of view. I mean, work is a form of energy, but what I want to talk about today is potential energy and connecting that with kinetic energy, which you've likely heard about. So when we think about, for example, a ball going up in the air, so it takes this kind of path, when we think about it from an energy point of view, we look at the work that I did on using my hand to release the ball, and then it goes up and it's got kinetic energy and potential energy. And so we're going to sort of talk our way through that. So if we think about this path of the golf ball that I threw up and then came back down, is that, okay, so I did work to send it up. From that point, so we're going to look at it from that point, from where it was released, we can have the ball, for example, it's got kinetic energy, and this is really at the bottom is when it has the highest kinetic energy because it's going the fastest and it slows down and then it picks it back up over here. So kinetic energy is maximum. Up here, it's not zero because I didn't throw it directly up. It had some speed going to the right. So kinetic energy is minimum. It's not zero. But we can think about what's happened to this kinetic energy is that it's gone into what we call potential energy or stored energy. So here, where kinetic energy is max, our potential energy, which we describe by U, I know, U is not anywhere in the word, but okay. And then this would be a U max, okay? And so this potential energy that we're talking about is really connected to the work that gravity is doing. Because when the ball is in the air, like here, the only force that's acting on it, we've neglected friction for an air resistance for right now, is just mg. So if we think about the work that's done by gravity, so the work done by the weight or the gravitational pull of the Earth, then we can say, well, the displacement is in this direction, displacement is in that direction, the force is down, so that would be m times g, force times displacement, times the angle between them, which would be 180 degrees, so cosine of 180 degrees, which is equal to -1. So I'm going to get rid of this and put a minus right there. So the work done as this travels is negative. And so the potential energy is a description of this work done by the weight, by the gravitational force. And so we say the potential energy, the change in potential energy, it's always a change in potential energy, for this force, the gravitational force, or any other force, is going to be minus the work that's done, because this became negative, and we're saying if this is a minimum, or like a zero, call it zero down here, then our potential energy at this point, is mg times the distance that we've gone. When we get to the maximum, if this is our maximum height, then this is going to be mg times the height. So in general, our expression is that our gravitational potential energy is mgy, because it's usually measured, we usually measure y as up and down, plus some constant. Okay, and this is always the case with potential energy because it's really about a difference in energy. We set the bottom to be equal to 0, but I could have set it to be like 500. Okay, if I set this to be 500 joules, then at the top I would have mgh plus 500 joules. Okay, so this is just a constant, whatever it is. Usually, we set y equals 0, we set the constant to be 0, just because that's easier. And so that's what I did here. Okay, so we're going to get rid of that 500 that we don't need. Now this could all be negative. I could have set this initial energy to be negative 500 or negative 5 million. And then up here, it would have been just mg times the height plus this negative 5 million if that's what I had chosen. Similarly, for a spring, we also have a potential energy. So with gravity, we have a potential energy. With a spring, potential energy associated with spring, it's minus the work. And if you remember the expression for work of a spring, we said was minus 1/2 k x squared, where we set x equals 0 at equilibrium. And so we do the same thing here. We say it's 1/2, of course it would be the other sign, kx squared plus a constant. Again, here we say x equals 0. That's our equilibrium. We would have mu is equal to 0. So we set x equals 0 as our equilibrium position. And so then that's our potential energy of a spring. This is our potential energy associated with gravity. So here we have the expressions the way you'll usually see them: potential energy, gravitational potential energy, and spring potential energy. And these are two forces that we can actually write a potential energy for. We can't do this for all forces. If we look at, say, taking something from down here up to here, so that's our displacement, and we take that as our displacement, or we take a path like this as our displacement. In both cases, the work done by gravity, right, because it points down, mg points down, is the same. In this case, you'd have mg times just this distance, and that would give us our work, which would be minus mg times d. And then over here, we would look at the component of the displacement, right? This would be the component of that piece of the displacement. This is a weird displacement. And then this one, also that one. So this would be like d2 and d3 if we wanted to follow these paths, but we would take the y components of these, and this is exactly the same value. In other words, the path doesn't matter, because this is what's called a conservative force. So a conservative force is one in which the work done is the same no matter the path. And if we have a conservative force, then we can write a potential energy associated with it. An example of a non-conservative force would be friction. Okay, so if we look at this as a top view of something going from one point to another point on a table, and we're pushing it, so here's our block and we're pushing it this way. If we go along this path versus, again, this path and this path, notice that on this path friction acts for one distance, but over here friction works along the path, and that's a longer path, because the friction force on this path looks like this, F sub k, but along this path, it goes like this, and it goes like this. So in this case, the longer path means more work done by friction, okay? So friction depends on the path, so this is a non-conservative force. And so there isn't a potential energy associated with friction. Okay, so non-conservative forces, we can't have potentials. These are the values that we have. I should put one other caveat here. This is for motion that's close to the Earth's surface. In other words, where this acceleration due to gravity really stays at 9.8 meters per second squared. And that's the case pretty much up to airplane heights and slightly beyond that. So you don't have to worry about this varying too much until we start looking at trying to get rockets to the moon and doing rocket science.